In this video, I'm going to talk about the reason why we want to combine many models when we're making predictions. If we have a single model, we have to choose some capacity for it. If we choose too little capacity, it won't be able to fit the regularities in the training data. And if we choose too much capacity, it will be able to fit the sampling error in the particular training set we have. By using many models, we can actually get a better trade-off between fitting the true regularities and overfitting the sampling error in the data. At the start of the video, I'll show you that when you average models together, you can expect to do better than any single model. This effect is largest when the models make very different predictions from each other. And at the end of this video, I'll discuss various ways in which we can encourage the different models to make very different predictions. As we've seen before, when we have a limited amount of training data, we tend to get overfitting. If we average the predictions of many different models, we can typically reduce that overfitting. This helps most when the models make very different predictions from one another. For regression, the squared error can be decomposed into a bias term and a variance term, and that allows us to analyze what's going on. The bias term is big if the model has too little capacity to fit the data. It measures how poorly the model approximates the true function. The variance term is big if the model has so much capacity that it's good at modeling the sampling error in our particular training set. So it's called variance because if we go and get another training set of the same size from the same distribution, our model will fit differently to that training set because it has different sampling error, and so we'll get variance in the way the models fit to different training sets. If we average models together, what we're doing is we're averaging away the variance, and that allows us to use individual models that have high capacity and therefore high variance. These high capacity models typically have low bias, so we can get the low bias without incurring the high variance by using averaging to get rid of the variance. So now let's try and analyze how an individual model compares with an average of models. On any one test case, some individual predictors may be better than the combined predictor. But different individual predictors will be better on different cases. And if the individual predictors disagree a lot, the combined predictor is typically better than all of the individual predictors when we average over test cases. So we should aim to make the individual predictors disagree without making them be poor predictors. The art is to have individual predictors that make very different errors from one another, but are each fairly accurate. So now let's look at the math of what happens when we combine networks. We're going to compare two expected squared errors. The first expected squared error is the one we get if we pick one of the predictors at random and use that for making our predictions. And then what we do is we average over all predictors the error we'd expect to get if we followed that policy. So y bar is the average of what all the predictors say, and yi is what an individual predictor says. So y bar is just the expectation over all the individual predictors I of yi, and I'm using those angle brackets to represent an expectation, where the thing that comes after the angle bracket tells you what it's an expectation over. We can write the same thing as 1 over n times the sum over all the n of the yi. Now, if we look at the expected squared error we get if we chose a predictor at random, what we'd have to do is compare that predictor with the target, take the squared difference, and then average that over all the predictors. That's what's on the left-hand side there. If I simply add a y bar and subtract a y bar, I don't change the value, and now it's going to be easier to do some manipulations. I can now multiply out that square, and inside these expectation brackets I have t minus y bar squared, yi minus y bar squared, and t minus y bar into yi minus y bar, which as we'll see will disappear. So the first term, t minus y bar squared, doesn't have an I in it anymore, and so we can forget about the expectation brackets for that. That really is t minus y bar squared. And that's the squared error you'd get if you compared the average of the models with the target. And our aim is to show the thing on the left-hand side is bigger than that, i.e. by using that average, we've reduced the expected squared error. So the extra term we have on the right-hand side is the expectation of yi minus y bar squared, and that's just the variance of the yi. It's the expected squared difference between yi and y bar. And then the last term disappears. It disappears because the difference of yi from y bar we expect to be uncorrelated with the difference between the error that the average of the networks makes and the target. And so we're multiplying together two things that are zero mean and uncorrelated, and we expect to get 0 on average. So the result is that the expected squared error we get by picking a model at random is greater than the squared error we get by averaging the models by the variance of the outputs of the models. That's how much we win by when we take an average. So I want to show you that in a picture. So along the horizontal line we have the possible values of the output, and in this case all of the different models predict a value that's too high. The predictors that are further than average from t make bigger than average squared errors, like that bad guy in red, and the predictors that are less than the average distance from t make smaller than average squared errors. And the first effect dominates because we're using squared error. So if you look at the math, let's suppose that the good guy and the bad guy were equally far from the mean. So the average squared error they make is y bar minus epsilon squared plus y bar plus epsilon squared. And when we work that out, we get the squared error that the mean of the predictors makes plus an epsilon squared. So we win by averaging predictors before we compare them with the target. That's not always true. It depends very much on using a squared error. If, for example, you have a whole bunch of clocks and you try and make them more accurate by averaging them all, that'll be a disaster. And it'll be a disaster because the noise you expect in clocks isn't Gaussian noise. What you expect is that many of them will be very slightly wrong, and a few of them will have stopped or will be wildly wrong. And if you average, you make sure they're all significantly wrong, which is not what you want. The same thing applies to the discrete distributions we have over class label probabilities. So suppose that we have two models, and one gives the correct label a probability of pi, and the other gives the correct label a probability of pj. Is it better to pick one model at random, or is it better to average those two probabilities and predict the average of pi and pj? Well, if our error measure is the log probability of getting the right answer, then the log of the average of pi and pj is going to be a better bet than the log of pi plus the log of pj averaged. That's most easily seen in a diagram because of the shape of the log function. So that black curve is the log. On the horizontal axis I've drawn pi and pj, and the gold-coloured line joins log pi to log pj. You can see that if we first average pi and pj together to get that average value where the blue arrow is, and then we compute the log, we get that blue dot. Whereas if we first take the log of pi and separately take the log of pj, and then we average those two logs, we get the midpoint of that gold line, which is below the blue dot. So to make this averaging be a big win, we want our predictors to differ by a lot. And there's many different ways to make them differ. You could just rely on a learning algorithm that doesn't work too well and get stuck in different local optima each time. It's not a very intelligent thing to do, but it's worth a try. You could use lots of different kinds of models, including ones that are not neural networks. So it makes sense to try decision trees, Gaussian process models, support vector machines. I'm not explaining any of those in this course. In Andrew Ng's machine learning course on Coursera, you can learn about all those things. Or you could try many other different kinds of model. If you really want to use a bunch of different neural network models, you can make them different by using a different number of hidden layers, or a different number of units per layer, or different types of unit. Like in some nets you could use rectified linear units, and in other nets you could use logistic units. You could use different types or strengths of weight penalty. So you might use early stopping for some nets, and an L2 weight penalty for others, and an L1 weight penalty for others. You could use different learning algorithms. So, for example, you could use full batch for some and mini batch for others if your dataset is small enough to allow that. You can also make the models differ by training the models on different training data. So there's a method introduced by Leo Breiman called bagging, where you train different models on different subsets of the data, and you get these subsets by sampling the training set with replacement. So we sampled a training set that had examples A, B, C, D, and E, and we got 5 examples, but we'll have some missing and some duplicated. And we train one of our models on that particular training set. This is done in a method called random forests that uses bagging with decision trees, which Leo Breiman was also involved in inventing. And when you train decision trees with bagging and then average them together, they work much better than single decision trees by themselves. In fact, the connect box uses random forests to convert information about depth into information about where your body parts are. We could use bagging with neural nets, but it's very expensive. If you wanted to train, say, 20 different neural nets this way, you'd have to get your 20 different training sets, and then it would take 20 times as long as training one net. That doesn't matter with decision trees because they're so fast to train. Also, at test time, you'd have to run these 20 different nets. Again, with decision trees, that doesn't matter because they're so fast to use at test time. Another method for making the training data different is to train each model on the whole training set, but to weight the cases differently. So in boosting, we typically use a sequence of fairly low capacity models, and we weight the training cases for each model differently. What we do is we upweight the cases that previous models got wrong, and we downweight the cases that previous models got right. So the next model in the sequence doesn't waste its time trying to model cases that are already correct. It uses its resources to try and deal with the cases the other models are getting wrong. An early use of boosting was with neural nets for MNIST, and there, when computers were much slower, one of the big advantages was that it focused the computational resources on modeling the tricky cases and didn't waste a lot of time going over easy cases again and again.
In this video, I'm going to talk about the mixture of experts model that was developed in the early 1990s. The idea of this model is to train a number of neural nets, each of which specializes in a different part of the data. That is, we assume we have a data set which comes from a number of different regimes, and we train a system in which one neural net will specialize in each regime, and a manager neural net will look at the input data and decide which specialists to give it to. This kind of system doesn't make very efficient use of data because the data is fractionated over all these different experts. And so with small data sets, it can't be expected to do very well. But as data sets get bigger, this kind of system may well come into its own because it can make very good use of extremely large data sets.
In boosting, the weights on the models are not all equal, but after we finish training, each model has the same weight for every test case. We don't make the weights on the individual models depend on which particular case we're dealing with. In mixtures of experts, we do. So the idea is that we can look at the input data for a particular case during both training and testing to help us decide which model we can rely on. During training, this will allow models to specialize on a subset of the cases. They then will not learn on cases for which they're not picked, so they can ignore stuff they're not good at modeling. This will lead to individual models that are very good at some things and very bad at other things. The key idea is to make each model, or expert as we call it, focus on predicting the right answer for cases where it's already doing better than the other experts. That will cause specialization. So there's a spectrum of models, from very local models to very global models. Nearest neighbours, for example, is a very local model. To fit it, you just store the training cases, so that's really simple. And then if you have to predict y from x, you simply find the stored value of x that's closest to the test value of x, and you predict the value of y that's the same as for the stored value. The result of that is that the curve relating the input to the output consists of lots of horizontal lines connected by cliffs. It would clearly make more sense to smooth things out a bit. At the other extreme, we have fully global models, like fitting one polynomial to all the data. They're much harder to fit to data, and they may also be unstable. That is, small changes in the data may cause big changes in the model you fit. That's because each parameter depends on all the data. In between these two ends of the spectrum, we have multiple local models that are of intermediate complexity. This is good if the dataset contains several different regimes, and those different regimes have different input-output relationships. In financial data, for example, the state of the economy has a big effect on determining the mappings between inputs and outputs, and you might want to have different models for different states of the economy. But you might not know in advance how to decide what constitutes different states of the economy. You're going to have to learn that too. So we have this problem, if we're going to use different models for different regimes, of how do we partition the dataset into these different regimes. In order to fit different models to different regimes, we need to cluster the training data into subsets, one for each of these regimes. But we don't want to cluster the data based on the similarity of input vectors. What we're interested in is the similarity of input-output mappings. So if you look at the case on the right, there's 4 data points that are nicely fitted by the red parabola, and another 4 data points that are nicely fitted by the green parabola. If you partition the data based on the input-output mapping, that is, based on the idea that a parabola will fit the data nicely, then you partition the data where that brown line is. If, however, you partitioned the data by just clustering the inputs, you'd partition it where the blue line is, and then if you look to the left of that blue line, you'd be stuck with a subset of data that can't be modelled nicely by a simple model. So I'm going to explain an error function that encourages models to cooperate, and then I'm going to explain an error function that encourages models to specialize. And I'm going to try to give you a good intuition for why these two different functions have these very different effects. So if you want to encourage cooperation, what you should do is compare the average of all the predictors with the target and train all the predictors together to reduce the difference between the target and their average. So using angle brackets for expectations again, the error would be the difference between the target and the average over all the predictors of what they predict. That will overfit badly. It'll make the model much more powerful than training each predictor separately, because the models will learn to fix up the errors that other models make. So if you're averaging models during training, and training so that the average works nicely, you have to consider cases like this. On the right, we have the average of all the models except for model I. So that's what everybody else is saying when their votes are averaged together. On the left, we have the output of model I. Now, if we'd like the overall average to be closer to the target, what do we have to do to the output of the ith model? Well, we have to move it away from the target. That will take the overall average towards the target. You can see that what's happening is model I is learning to compensate for the errors made by all the other models. But do we really want to move model I in the wrong direction? Intuitively, it seems better to move model I towards the target. So here's an error function that encourages specialization, and it's not very different. To encourage specialization, we compare the output of each model with the target separately. We also need to use a manager to determine the weight we put on each of these models, which we can think of as the probability of picking each model if we had to pick one. So now our error is the expectation over all the different models of the squared error made by that model times the probability of picking that model, where the manager or gating network is determining that probability by looking at the input for this particular case. What will happen if you try and minimize this error is that most of the experts will end up ignoring most of the targets. Each expert will only deal with a small subset of the training cases, and it will learn to do very well on that small subset. So here's a picture of the mixture of experts architecture. Our cost function is the squared difference between the output of each expert and the target, averaged over all the experts, but with the weights in that average determined by the manager. There's actually a better cost function we'll come to later based on a mixture model, but this was the cost function I first thought of, and I think it's easier to explain the intuition with this cost function. So we have an input. Our different experts all look at that input. They all make their predictions based on that input. In addition, we have a manager. The manager might have multiple layers, and the last layer of the manager is a softmax layer. So the manager outputs as many probabilities as there are experts. And using the outputs of the manager and the outputs of the experts, we can then compute the value of that error function. If we look at the derivatives of that error function, the outputs of the manager are determined by the inputs xi to the softmax group in the final layer of the manager, and then the error is determined by the outputs of the experts and also the probabilities output by the manager. If we differentiate that error with respect to the outputs of an expert, we get a signal for training that expert. And that gradient that we get with respect to the output of an expert is just the probability of picking that expert times the difference between what that expert says and the target. So if the manager decides that there's a very low probability of picking that expert for that particular training case, the expert will get a very small gradient, and the parameters inside that expert won't get disturbed by that training case. It'll be able to save its parameters for modeling the training cases where the manager gives it a big probability. We can also differentiate with respect to the outputs of the gating network, and actually what we're going to do is differentiate with respect to the quantity that goes into the softmax. That's called the logit, that's xi. And if we take the derivative with respect to xi, we get the probability that that expert was picked times the difference between the squared error made by that expert and the average over all experts when you use the weighting provided by the manager of the squared error. So what that means is, if expert I makes a lower squared error than the average of the other experts, then we'll try to raise the probability of expert I. But if expert I makes a higher squared error than the other experts, we'll try and lower his probability. That's what causes the specialization. Now there's actually a better cost function. It's just more complicated. It depends on mixture models, which I haven't explained in this course. Again, those will be well explained in Andrew Ng's course. I did explain, however, the interpretation of maximum likelihood when you're doing regression as the idea that the network is actually making a Gaussian prediction. That is, the network outputs a particular value, say y1, and we think of it as making bets about what the target value might be that are a Gaussian distribution around y1 with unit variance. So the red expert makes a Gaussian distribution of predictions around y1, and the green expert makes a Gaussian prediction around y2. The manager then decides probabilities for the two experts, and those probabilities are used to scale down the Gaussians. Those probabilities have to add to 1, and they're called mixing proportions. And so once we've scaled down the Gaussians, we get a distribution that's no longer a Gaussian. It's the sum of the scaled down red Gaussian and the scaled down green Gaussian. And that's the predictive distribution for our mixture of experts. What we want to do now is maximize the log probability of the target value under that black curve. And remember, the black curve is just the sum of the red curve and the green curve. So that leads to the following model for the probability of a target given a mixture of experts. The probability is on the left, and it's the sum over all the experts of the mixing proportion assigned to that expert by the manager or gating network times e to the minus the squared difference between the target and the output of that expert, scaled by the normalization term for a Gaussian with a variance of 1. And so our cost function is simply going to be the negative log of that probability on the left. We're going to try and minimize the negative log of that probability.
In this video, I'm going to return to the idea of full Bayesian learning and explain a little bit more about how it works. And then in the following video, I'm going to show how it can be made practical.
In full Bayesian learning, we don't try and find a single best setting of the parameters. Instead, we try and find the full posterior distribution over all possible settings. That is, for every possible setting we want a posterior probability density, and all those densities we want to add up to 1. It's extremely computationally intensive to compute this for all but the simplest models. So in the example earlier, we did it for a biased coin which just has one parameter, which is how biased it is. But in general, for a neural net, it's impossible. After we've computed the posterior distribution across all possible settings of the parameters, we can then make predictions by letting each different setting of the parameters make its own prediction, and then averaging all those predictions together, weighting by their posterior probability. This is also very computationally intensive. The advantage of doing this is that if we use the full Bayesian approach, we can use complicated models even when we don't have much data. So there's a very interesting philosophical point here. We're now used to the idea of overfitting when you fit a complicated model to a small amount of data. But that's basically just a result of not bothering to get the full posterior distribution over the parameters. So a frequentist would say, if you don't have much data, you should use a simple model. And that's true. But it's only true if you assume that fitting a model means finding the single best setting of the parameters. If you find the full posterior distribution, that gets rid of overfitting. If there's very little data, the full posterior distribution will typically give you very vague predictions, because many different settings of the parameters that make very different predictions will have significant posterior probability. As you get more data, the posterior probability will get more and more focused on a few settings of the parameters, and the posterior predictions will get much sharper. So here's a classic example of overfitting. We've got 6 data points, and we fitted a 5th order polynomial, and so it should go exactly through the data, which it more or less does. We also fitted a straight line, which only has 2 degrees of freedom. And so which model do you believe? The model that has 6 coefficients and fits the data almost perfectly, or the model that only has 2 coefficients and doesn't fit the data all that well? It's obvious that the complicated model fits better, but you don't believe it. It's not economical, and it also makes silly predictions. So if you look at the blue arrow, if that's the input value and you're trying to predict the output value, the red curve will predict a value that's lower than any of the observed data points, which seems crazy, whereas the green line will predict a sensible value. But everything changes if instead of fitting one 5th order polynomial, We start with a reasonable prior over fifth order polynomials, for example that their coefficients shouldn't be too big, and then we compute the full posterior distribution over fifth order polynomials. I've shown you some samples from this distribution in the picture, where a thicker line means higher probability in the posterior. So you'll see some of those thin curves miss a few of the data points by quite a lot, but nevertheless they're quite close to most of the data points. Now we get much vaguer but much more sensible predictions. So where the blue arrow is, you'll see the different models predict very different things, and on average they make a prediction quite close to the prediction made by the green line. From a Bayesian perspective, there's no reason why the amount of data you collect should influence your prior beliefs in the complexity of the model. A true Bayesian would say, you have prior beliefs about how complicated things might be, and just because you haven't collected any data yet, it doesn't mean you think things are much simpler. So we can approximate full Bayesian learning in a neural net if the neural net has very few parameters. The idea is we put a grid over the parameter space. So each parameter is only allowed a few alternative values, and then we take the cross product of all those values for all the parameters, and now we get a number of grid points in the parameter space. And at each of those points we can see how well our model predicts the data. That is, if we're doing supervised learning, how well our model predicts the target outputs. And we can say that the posterior probability of that grid point is the product of how well it predicts the data, how likely it is under the prior, and with the whole thing normalized so that the posterior probability is out to 1. This is still very expensive, but notice it has some attractive features. There's no gradient descent involved, and there's no local optimum issues. We're not following a path in this space, we're just evaluating a set of points in the space. Once we've decided on the posterior probability to assign to each grid point, we then use them all to make predictions on the test data. That's also expensive, but when there isn't much data, it'll work much better than maximum likelihood or maximum a posteriori. So the way we predict the test output, given the test input, is we say the probability of a test output, given a test input, is the sum over all the grid points of the probability that that grid point is a good model, is the sum over all grid points of the probability of that grid point, given the data and given our prior, times the probability that we would get that test output given the input and given the grid point. In other words, we have to take into account the fact that we might add noise to the output of the net before producing the test answer. So here's a picture of full Bayesian learning. We have a little net here that has 4 weights and 2 biases. If we allowed 9 possible values for each of those weights and biases, there'd be 9 to the 6 grid points in the parameter space. It's a big number, but we can cope with it. For each of those grid points, we'd compute the probability of the observed outputs on all the training cases. We'd multiply by the prior for the grid point, which might depend on the values of the weights, for example, and then we'd renormalize to get the posterior probability over all the grid points. Then we make predictions using those grid points, but weighting each of their predictions by its posterior probability.
In this video, I'm going to describe how to make full Bayesian learning practical for neural networks that have thousands and perhaps even millions of weights. The technique that's used is a Monte Carlo method, which seems very odd the first time we hear about it. We use a random number generator to move around the space of weight vectors in a random way, but with a bias towards going downhill in our cost function. If we do this right, we get a beautiful property, which is that we sample weight vectors in proportion to their probability in the posterior distribution. And that means by sampling a lot of weight vectors, we can get a good approximation to the full Bayesian method.
The number of grid points is exponential in the number of parameters, so we can't make a grid for more than a few parameters.
If there's enough data so that most of the parameter vectors are very unlikely, only a tiny fraction of the grid points will make a significant contribution to the predictions. So maybe we can just focus on evaluating this tiny fraction if we can find it. An idea that makes Bayesian learning feasible is that it might be good enough just to sample weight vectors according to their posterior probabilities. So if you look at this equation, the probability that we assign to a test output, given the input for the test case and the training data, is the sum over all points in weight space of the posterior probability of that point in weight space given the training data, times the probability distribution for the test values that we predict given that point in weight space Wi and given the test input. Now, instead of adding up all the terms in that sum, we could just sample terms from that sum. What we do is we sample the weight vectors in proportion to that probability. So either we sample them or we don't. So they'll get a weight of 1 or 0. But the probability of getting a 1, that is the probability of being sampled, will be their posterior probability. So that will give us the correct expected value for the right-hand side. It'll have noise due to the sampling, but it'll have the correct expected value. So here's a picture of what happens in standard backpropagation. On the right I've drawn the weight space, which of course is very high dimensional and unbounded, and this is a very bad picture of it, but it's the best I can do. In this weight space I've drawn some contours, which are meant to be contours of equal values of our cost function, and the way backpropagation is normally used is we start with some small value of the weights, and then we follow the gradient. We move downhill in our cost function in the direction that increases the log likelihood plus the log prior summed over all training cases. Eventually, we'll either end up in a local minimum, or we'll get stuck on a plateau, or we'll just move so slowly that we run out of patience. But the main point of this picture is that we follow a path from an initial point to some final single point. Now, if we're using a sampling method, what we could do is start at the same place as we did before, but each time we update the weights, we add a bit of Gaussian noise, so we're jittering around. The weight vector will never settle down then. It'll keep on moving around. It'll wander over the space, but always preferring low-cost regions. That is, it'll tend to go downhill if it can. An important question is whether we can say anything about how often the weights will visit each point in that space. So the red dots are meant to be samples we took of the weights as we wandered around the space, and the idea is we might save the weights after every 10,000 steps. And if you look at those red dots, a few of them are in high-cost regions, because those regions are quite big. The deepest minimum has the most red dots, and other minima also have red dots. The dots aren't right at the bottom of a minimum because they're noisy samples. If we add that Gaussian noise in just the right way, there's a wonderful property of Markov Chain Monte Carlo. It's an amazing fact. The weight vectors, if we've wandered around for long enough, will be unbiased samples from the true posterior distribution over weight vectors. That is, those red dots we saw on the previous slide will be samples from the posterior, where weight vectors that are highly probable under the posterior are much more likely to be represented by a red dot than weight vectors that are highly improbable. This is called Markov Chain Monte Carlo, and it makes it feasible to use Bayesian learning with thousands of parameters. The method I suggested of adding some Gaussian noise is called the Langevin method, and it's not the most efficient method. There's more sophisticated methods that are more efficient, and what I mean by more efficient is they don't need to wander around the weight space for so long before you can start taking those red samples. Full Bayesian learning can actually be done with mini batches.
When we compute the gradient of the cost function on a random mini-batch, we're going to get an unbiased estimate but with sampling noise. And the idea is to use that sampling noise to provide the noise that a Markov Chain Monte Carlo method needs. It's a very clever idea. Recently, Welling and his collaborators made it work nicely so that they could fairly efficiently get samples from the posterior distribution over weights using mini-batch methods. This should make it possible to use full Bayesian learning for much larger networks, where you have to train them with mini-batch to have any hope of ever finishing training them.
In this video, I'm going to describe a new way of combining a very large number of neural network models without having to separately train a very large number of models. This is a method called Dropout that's recently been very successful in winning competitions. For each training case, we randomly emit some of the hidden units, so we end up with a different architecture for each training case. We can think of this as having a different model for every training case, and then the question is, how could we possibly train a model on only one training case? And how could we average all these models together efficiently at test time? The answer is that we use a great deal of weight sharing.
I want to start by describing two different ways of combining the outputs of multiple models. In a mixture, we combine models by averaging their output probabilities. So if model A assigns probabilities of 0.3, 0.2 and 0.5 to three different answers, and model B assigns probabilities of 0.1, 0.8 and 0.1, the combined model simply assigns the averages of those probabilities. A different way of combining models is to use a product of the probabilities. Here we take a geometric mean of the same probabilities. So model A and model B again assign the same probabilities as they did before. But now what we do is we multiply each pair of probabilities together and then take the square root. That's the geometric mean. And the geometric means will generally add up to less than 1, so we have to divide by the sum of the geometric means to normalize the distribution so that it adds up to 1 again. You'll notice that in a product, a small probability output by one model has veto power over the other models. Now I want to describe an efficient way to average a large number of neural nets that gives us an alternative to doing the correct Bayesian thing. The alternative probably doesn't work quite as well as doing the correct Bayesian thing, but it's much more practical. So consider the neural net with one hidden layer shown on the right. Each time we present a training example to it, what we're going to do is randomly emit each hidden unit with a probability of 0.5. So we crossed out 3 of the hidden units here. And we run the example through the net with those hidden units absent. What this means is we're randomly sampling from 2 to the h architectures, where h is the number of hidden units. It's a huge number of architectures. Of course, all of these architectures share weights. That is, whenever we use a hidden unit, it's got the same weights as it has in other architectures. So we can think of Dropout as a form of model averaging. We sample from these 2 to the h models. Most of the models, in fact, will never be sampled. And a model that is sampled only gets one training example. That's a very extreme form of bagging. The training sets are very different for the different models, but they're also very small. The sharing of the weights between all the models means that each model is very strongly regularized by the others. And this is a much better regularizer than things like L2 or L1 penalties. Those penalties pull the weights towards 0. By sharing weights with other models, a model gets regularized by something that's going to tend to pull the weights towards the correct value. The question still remains what we do at test time. So we could sample many of the architectures, maybe 100, and take the geometric mean of their output distributions. But that will be a lot of work. There's something much simpler we can do. We use all of the hidden units, but we halve their outgoing weights. So they have the same expected effect as they did when we were sampling. It turns out that using all of the hidden units with half their outgoing weights exactly computes the geometric mean of the predictions that all 2 to the h models would have used, provided we're using a softmax output group. If we have more than one hidden layer, we can simply use dropout of 0.5 in every layer. At test time, we halve the outgoing weights of all the hidden units, and that gives us what I call the mean net. So we use a net that has all of the units, but the weights are halved. When we have multiple hidden layers, this is not exactly the same as averaging lots of separate dropped-out models, but it's a good approximation and it's fast. We could run lots of stochastic models with dropout and then average across those stochastic models, and that would have one advantage over the mean net. It would give us an idea of the uncertainty in the answer. What about the input layer? Well, we can use the same trick there too. We use dropout on the inputs, but we use a higher probability of keeping an input. This trick's already in use in a system called denoising autoencoders, developed by Pascal Vincent, Hugo Larochelle and Yoshua Bengio at the University of Montreal, and it works very well. So how well does dropout work? Well, the record-breaking object recognition net, developed by Alex Krzyzewski, would have broken the record even without dropout, but it broke it by a lot more using dropout. In general, if you have a deep neural net and it's overfitting, dropout will typically reduce the number of errors by quite a lot. I think any net that requires early stopping in order to prevent it overfitting would do better by using dropout. It would of course take longer to train, and it might need more hidden units. If you've got a deep neural net and it's not overfitting, you should probably be using a bigger one and using dropout. That's assuming you have enough computational power. There's another way to think about dropout, which is how I originally arrived at the idea. And you'll see it's a bit related to mixtures of experts and what's going wrong when all the experts cooperate. What's preventing specialization? So if a hidden unit knows which other hidden units are present, it can co-adapt to the other hidden units on the training data. What that means is the real signal that's training a hidden unit is try to fix up the error that's left over when all the other hidden units have had their say. That's what's being backpropagated to train the weights of each hidden unit. Now that's going to cause complex co-adaptations between the hidden units, and these are likely to go wrong when there's a change in the data. So on new test data, if you rely on a complex co-adaptation to get things right on the training data, it's quite likely to not work nearly so well on new test data. It's like the idea that a big complex conspiracy involving lots of people is almost certain to go wrong, because there's always things you didn't think of. And if there's a large number of people involved, one of them will behave in an unexpected way, and then the others will be doing the wrong thing. It's much better, if you want conspiracies, to have lots of little conspiracies. Then when unexpected things happen, many of the little conspiracies will fail, but some of them will still succeed. So by using dropout, we force a hidden unit to work with combinatorially many other sets of hidden units. And that makes it much more likely to do something that's individually useful, rather than only useful because of the way particular other hidden units are collaborating with it. But it's also going to tend to do something that's individually useful and is different from what other hidden units do. It needs to do something that's marginally useful given what its co-workers tend to achieve. And I think this is what's giving nets with dropout their very good performance.